Welcome, everybody. Good afternoon. Welcome to the second YorRobots Venables poster exhibition. This event is associated with the Venables Internship program. So, first of all, I'd like to thank our sponsor, Phil Venables. He is the one that enables via the connection with our computer science departmental administrator, Jane Lawrence, who's here with us this afternoon, fund this program of internships, which allows that a group of about 15 students work over the summer together with academics from across the university to do some interesting research work in the area of robotics. So thank you for our sponsors. Thanks also to the YorRobots team, Don Forrester, Amanda Morris, and Johnny McCartney, who are here this afternoon, but also have been supporting the internship program throughout the year. Thank you so much to you all for the Venables initiative and everything else you do for the YorRobots network. I guess most of you, if not all of you, you have heard of YorRobots. It's the network of researchers at all levels working in University of York in the area of robotics. So this afternoon, we have a program, a very exciting program of presentations where the students who held this internship over the summer are going to present a poster summarizing the work that they have done with the academics. In the case of a few students, unfortunately, for a variety of reasons, they were not able to be here this afternoon, but their supervisors have kindly agreed to step in and present that poster or say something about their work. After that, we are going to have some time to go and talk to the poster presenters. There are breakout rooms, and we will have chosen your breakout rooms, and I believe you will be able to move across breakout rooms as well if you want, and to have a chat with the poster presenters. We will also go around, and we, as the judging panel, joining me this afternoon, we have two other members of the YorRobots Executive Committee, Keith Allen. Hello, Keith. And Darren, where are you, Darren? Darren Reed here. So Keith from the Department of Philosophy, Darren Reed from the Department of Sociology. Robotics research in the University of York is extremely multidisciplinary, and their presence here is a demonstration of that. And I'm very grateful to the two of them as well for joining me in the judging panel this afternoon. So we as judges go around every breakout room and talk to every student. Afterwards, we are joining to attend a talk by Alvaro Miyazawa. You may have seen in the program that originally we had a talk from Simon Foster, but unfortunately Simon is not very well today, and Alvaro has very kindly agreed to step in at the last moment. Alvaro, thank you very much. Alvaro is also a member of the same group, of the RoboStar group, which is the Center of Excellence on Software Engineering for Robotics at the University of York and in several other universities. So Alvaro is a member of that same group, and he's going to give you a talk called Robochart, Modeling and Verification of Robotic Applications. It's in the same line of work as Simon would have presented, and as I say, we're very grateful to Alvaro for stepping in the last minute. Now, we are very tight for time. Each student and each presenter has about 3 minutes to present their poster. Our first student who will present their work is Isobel Stanton. Is Isobel here? Hello, Izzy Stanton. Izzy, I'm going to share my screen and present your poster. To make things quicker, can people see the poster? Yeah? Easy, please go ahead. 3 minutes, please.
Great. Thank you so much. I hope everyone can hear me okay.
We can.
So the title of my research project is Robot Assisted Surgery, a Waste of Resources or the Future of Healthcare. The aim was to explore whether and to what extent our assignment of moral responsibility changes when comparing traditional laparoscopic surgery, which is just a fancy way of saying keyhole surgery, and surgery performed using the Da Vinci robot. Due to their direct contact with people in vulnerable positions, a high level of concern is justified. It is essential that surgical robots are safe for use, and if harm is caused, there is someone who can be held responsible. Moral responsibility can be understood as the state of deserving praise or blame for an action and its consequences. There are three key conditions to holding someone morally responsible. Firstly, they must have the capacity to tell right from wrong. Secondly, they must have control over their actions, meaning they weren't forced to act by anyone else. A person may be causally responsible for physically instigating harm, but if it wasn't their intention, they might not be deserving of blame. Finally, they must have sufficient knowledge of what they are doing and the potential consequences that their action could result in. So, what bearing does this have on surgery? Keeping patients safe is the primary concern of all healthcare workers. But during surgery, the care of the patient is specifically allocated to the surgeon assigned to that procedure. Despite having a team of surgical assistants and nurses working with them, it is the surgeon who is morally responsible for ensuring tasks like suturing, for example, are performed to their satisfaction. If one member of the surgical team makes a mistake, the surgeon, as the team leader, is blameworthy. The Da Vinci surgical robot is one of the most well-known and widely used surgical robots in the world. It consists of a console from which the surgeon operates the robot using handheld controls, similar to using a remote control car or drone. These controls also move the 3D camera connected to the vision cart, enabling the surgical team to view the operating area clearly without getting in each other's way. The operating table is where the patient is positioned beneath the arms of the robot, the frame for the tools and camera. As you can see from my poster, there are advantages to the Da Vinci robot, such as increased visibility and less strenuous procedures for the surgeon. However, there is some cause for concern, as there have been cases where the robot has continuously displayed error messages, resulting in its use being abandoned and the surgeon having to manually complete the operation. The time taken to extract the robot and prepare for traditional surgery has resulted in long-term damage to some patients. In another case, the Da Vinci robot lost power, becoming completely unresponsive, resulting in it being stuck inside the patient for quite some time. So, who should be held responsible if harm were to be caused? I explained earlier that in traditional surgery, the surgeon is blameworthy for harm caused to the patient. But when considering where responsibility lies with surgical robots, the manufacturer of the robot also needs to be considered a potential candidate for blame, as harm could be caused outside the surgeon's control if, for instance, the robot itself is faulty. It would be unreasonable to blame the surgeon when the manufacturer deployed an unsafe robot. To summarize, there is a significant change to our understanding of responsibility in the event of harm between traditional and robot-assisted surgery. In the former, the surgeon alone deserves blame. In the latter, the manufacturer and the surgeon are both potential candidates for blame. Who is deserving of blame just depends on the circumstances. So whether the error is on behalf of a member of the surgical team, the surgeon is blameworthy, or on behalf of the robot itself being unfit for purpose, making the manufacturer blameworthy. To put my project into some greater context, understanding where moral responsibility lies in the event of harm, both in traditional and robot-assisted surgery, helps to keep track of how assignments of praise and blame change over time and with new technological advancements. The future of surgical robotics is likely to be focused on autonomous robots, having robots perform tasks or even entire operations while needing no intervention from a surgeon, radically altering how operations are performed. This prompts the question, who would be to blame if harm occurs? Understanding where moral responsibility currently lies functions as a useful foundation for where it may lie in the future. Thank you for listening.
Thank you very much, Izzy.
Thank
Very
you.
interesting work, lots of questions We meet in the breakout room, and I hope others will join as well to talk about your work. Thank you. The next student is Emily Wood. Is Emily there?
Hi, I'm here, yeah.
Hi, Emily.
Hi.
I hope that your poster is now visible.
I don't know, it's not available on my screen, but I don't know about anyone else. Oh, okay, there we go, that's fine.
Okay. Please.
Okay.
Go ahead.
Yeah, so I'm a psychology student, so I decided to apply my knowledge of psychology to robotics and investigate personality in social robots. So social robots are robots that are used to communicate with other humans and take over the roles that humans would usually play in settings such as care homes, in teaching settings, things like that. So I wanted to look into how we can manipulate the personality of the robot to make them more trusting and likable by the users. So I had some research done before I started my own project. So I had a look at the literature already available. And I found that some research had already been done into robot personality. And they found that elderly people actually feel more willing to open up to robots than they do to humans sometimes. So that was very interesting, as these care robots are being moved into care homes. And obviously, as older people are from an older generation, they might not be so comfortable introducing robots into their lives. So I found that really interesting, that perhaps robots could be integrated into these environments. The personality type I wanted to focus on was neuroticism, as those people find it particularly hard to trust. So that was the personality that my research centered around. And I based my research on the theory that people tend to like people that are similar to themselves. So my thought was that neurotic individuals might like a robot that has neurotic traits within it. So neuroticism generally, if you don't know, these people tend to be more cautious and withdrawn. So they do find it harder to trust. So in the robot, obviously, I didn't want to take any negative aspects of the neurotic trait. I tried to put in aspects such as caution, risk aversion, things that might make a neurotic individual feel more comfortable. So for my research, I designed 2 robots using the software Furhat SDK. The picture at the bottom of the poster is an example of what the robots looked like. They're just virtual robots on a screen. And I coded them to have 2 separate personalities. So one was neurotic and one was open to experience, which was my control robot. And what I got the participants to do was play some card games with each robot to interact with them and get a feel for their personality. And then I'd also measure the participants' personality. And then after they'd been introduced to both robots, they had to report which they preferred more and which they felt they could trust more. So what I found from that was actually that individuals preferred an open robot generally. The neurotic robot wasn't very popular. But interestingly, the personalities of both robots did come through purely from manipulating the dialogue and facial expressions of both robots, which is a really interesting finding that will have a lot of interesting applications for designing robots in the future. So participants generally seem to trust, and feel more similar to the open robot, and they're also more willing to open up to it. Interestingly, I did find that participants who themselves were open to experiences preferred the robot of the same personality. So that did confirm my thoughts at the beginning, that people would like a robot that was more similar to themselves. Just unfortunately, I didn't find that for neurotic individuals. So perhaps a neurotic robot isn't particularly likable. I also found that participants took more risks in the card games when playing with the open to experiences robot, which again will have some really interesting applications for things like gambling and risk taking, because the personality of the robot actually altered the behavior of the participant. So that was really interesting. And finally, I just found that open robots were also deemed more suitable to a variety of different roles for care robots, such as care, disaster response, education training, and hospitality. So yeah, that's what I found. And I look forward to answering any questions that you have.
Okay, thank you very much, Emily.
Thank you.
Very nice. We talk in the breakout rooms, as I mentioned. So the next student is Harry Vargas. Is Harry there?
Yes, I am. Hi.
Oh, hello. Hi there, Harry.
Hi.
Hope you can see your poster.
Yes, I can. Thanks.
Please.
So, yeah, so the project I worked on was about generating kinematic equations for robot manipulators. And the aim of this project was to find implementations which already exist that have algorithms to derive kinematic equations for robots, and then to evaluate how we can manipulate them to apply robot models defined in SD format. And SD format stands for Simulation Description Format. This is a XML-based language used to describe objects and environments for simulators for robots. So once you have an SD format file, you can input this in a simulator to visualize the robot model. And kinematic equations in this context essentially is the process of obtaining the position and orientation of the end effector of a robotic arm, so the end point of it, given the known joint angles and angular velocities. And so in this project, I've coded a program that takes a model of a robotic arm defined in simulation description format to output a transformation matrix, which essentially describes the position and orientation of the endpoint of the arm. And to summarize how I did this, I first had to extract the elements we need specified in SD format using an XML parser. And then I calculated the kinematic equations by building rotation and transformation matrices for each part of the robotic arm. And then I combined these to build a binary transformation matrix. And I was able to run a few tests. So in the results section, you can see the visual and descriptive outputs. So when I inputted a robotic arm with 2 links and a joint, and taking the individual parts of the arm and the angles between them, the output transformation matrix shows the coordinate positions of where the end effector for that arm is and the angles that it's oriented in the 3D plane. And the original scope of the project was to also take into account different types of joints that can be present in the robotic arm, as well as the forces that act on it. So this would be a future area for development of my program, but this is what I was able to achieve overall in the 8-week timeframe. So yeah.
Okay, thank you very much, Harry. Your poster doesn't say who your supervisors were. Can you just say that for the benefit of the audience?
Yes, sorry. So it's Mark Host and Alvaro.
Okay, all right. Thank you very much. We talk in the breakout room. Thank you. The next student is Charlie Wilson. I don't have a poster for Charlie. Is Charlie there? I don't think Charlie.
I don't think Charlie's here.
No. Okay, right. So the next student is Lucas Williamson.
Yeah. Hi.
Is there? Okay, Lucas. Hopefully you can see your poster.
Yeah. Hi.
Okay.
My project was on the decentralized mapping with the PyPuck robotics platform. Just to give some motivation, mapping and localization with a swarm robotics platform is an open problem, and it can be used to tackle problems such as exploration of hazardous areas. Those centralized systems do exist and have existed for some time. Decentralized solutions are still lacking. Whilst some domain-specific implementations exist, they can't be applied generally. So the essence of this project was taking the PyPark robotics system developed by the University of York, which has a higher computational capability than traditional small swarm scale platforms like the ePark, and applying it to this problem using ROS or ROS2, which is an open source robotics framework that provides hardware abstraction. So this can provide a scalable, transferable, and shareable solution for the future. Due to COVID, the majority of this work was carried out online. So I modeled the PyPark robots in a software called YorRobots. In the summary section, you can see a brief picture like of the robot within the simulation. Okay, so this project was basically 3 parts. I coded 3 different swarm like mapping algorithms. Traditionally, very simple algorithms such as random walk have been effective at displaying decentralized mapping. So I started with fairly simplistic algorithms, and then I built up to see if I could increase the efficiency. I coded a wall bouncing algorithm and an obstacle avoidance with an element to random walk, which basically is just some random deviation, and a frontier exploration algorithm, which basically looks at the generated map and creates targets to head to. So that was part 1. Part 2 was basically the map creation. Previous research with the PyParks used a simultaneous localization and mapping method, or SLAM, called G-mapping. This provided to be quite coherent, so I also used that. And then the third part was the localization. This was created from the odometry data, which was a fusion of a wheel encoder, so just counting the wheel steps, and an IMU, which is like an inertial measurement unit. So that includes things like accelerometers. I then ran these on multiple different environments, one being a maze, one being an automated office environment, and one being a control. And I defined a set of statistics and an experimental method based on building a ROS testbed by Z et al., where they aim to standardize mapping experimentation with ROS. Okay? And in regards to my results, unfortunately, since this couldn't be actualized on hardware, all the code and methods has been documented, and since it's used in ROS, this can be simply applied to hardware when it's ready. And just to summarize, so I created a system for mapping and localization in multiple environments with a PyPark robotics platform, which can be generalized and expanded to different configurations and robots. Thank you.
Thank you very much, Lucas. All right, we chat. Hopefully we'll have loads of people visiting you. We chat in the breakout rooms. The next student is William Burbidge. Is William there?
I am. Okay.
William, I'm finding it very hard to hear you.
I thought that. Is that any?
Yeah. Okay. No, it got better. Now it's very quiet again.
Okay, sorry about this.
That's better now. Hopefully you can see your poster. Please go ahead.
I'll just be a minute, but still seems.
Can't hear you.
Can you hear me okay now?
We could, yes.
Okay, cool. I'll start then.
Please.
Hi, I'm William, and I'm presenting Supercapacitor powered robotics. The main aim of the project was looking at the feasibility of utilizing supercapacitors as an alternative for lithium batteries. There are a range of benefits for this, including a far higher charge-to-use ratio due to the very low resistance, and because of this, more efficient charge and discharge, high power density, higher safety, and an alternate to the use of conflict resources in lithium batteries. Because the energy density is considerably lower than that of lithium cells, the focus application was for situations that require high uptime, which could be split into cycles, such as a tram going from stop to stop or a drone sanitizing a room and docking to a charger. The prior is the current use of supercapacitors, although the problem is that supercapacitors aren't always being used as efficiently as they could be. This is because the voltage of a supercapacitor drops linearly through a cycle, meaning that often a large part of the supercapacitor is being unutilized. Therefore, a considerable element of the research was looking at the commercial feasibility of the design of a discrete step-up conversion circuit along with a supercapacitor in comparison to a battery. Due to this aim, I thought a holistic approach, considering factors such as availability, cost, weight, and electrical characteristics, as well as efficiency, would be most beneficial. It wasn't the easiest of times to do a project looking at the design of a circuit where considerable sections were semiconductor based due to the ongoing semiconductor shortages. This meant a considerable amount of time was spent on redesign. I do feel that this was beneficial though, as it challenged myself to look at alternate designs and build a greater understanding of individual elements of the design. I do feel it made for a better end product, even though it's difficult and sometimes restricted the development journey. I will give just a quick run through now of development decisions alongside the poster, which you can see for more information. So I needed to design a circuit that could provide a constant output voltage akin to a lithium cell. Ensuring as high a percentage of the capacitor's energy could be utilized as possible was important. So the design of the circuit was made so it could work as low as 0.6 volts, allowing around 96% energy utilization. I designed a synchronous step-up circuit using efficient MOSFETs, capacitors, and inductors, and then designed a custom 4-layer circuit board as a way of limiting parasitics. I'm now looking at the development of a second design, which is focusing on a low-cost drone. I'd like to thank my supervisors, Martin and Zion, for all the support, as well as the members of the YorRobots team. Thank you for listening.
And thank you for doing the work and coming today. Thank you, William. Right, thank you. So the next student is Chayaban Limpabandhu. I think Chayaban wants to share his own screen. So Chayaban, are you there? Yes, you are. I will stop sharing. Please share your screen as soon as you can.
Thank you. Can you all see my screen?
Yes, we can.
Yeah. So our overall arching project objective is to organize a micromouse robotics competition at the University of York. This will encourage students to learn about robotics and coding in peer-driven environment, increase participation in STEM activities, and support female and underrepresented minority students to participate in STEM. YorRobots and Department of Electronics Engineering are co-sponsoring the competition, which takes place from November to March. Figure 2 shows the statistic of 51 participants, including 27% of female students and 6 different departments. Majority is from engineering and computer science. To assist students with no engineering background, we set up a self-learning material, design consultations, and weekly newsletter. which involve designing and sharing open source hardware and software that implement an algorithms for finding the optimal path through the maze. We also have provided an example of modifying a commercially available robot, Pololu 3.5 robot, which is a low-cost motorized mobile platform with 2 motors, 5 infrared sensors, a microprocessor, and LCD display. To control this robot motion, a pair of optical encoders were added to the wheel of the robot. To explore the maze, 4 infrared sensors were added to the robot to detect surrounding walls, intersections, and dead end of the maze. To solve the maze, the fat field algorithm was used by the robot to solve the shortest route. We have so far completed the first kickoff event in November. Followed by this, they are going to have 1 consultation event, 2 practice events, and then the final competition in late March. We hope this will be a successful event to promote STEMs and robotics at our universities. Thank you.
Thank you. Thank you, Shaban. Yes, the competition is on now, and perhaps people around this room might be interested. I believe it is still possible to join. It's another one of the YorRobots activities with the help there of Shaban and the electronic engineering department. Do join if you can. Okay, so if you could stop sharing, Shaban, the next student is Nikita Jandu. I will share my screen with Nikita's poster. There it is. Hopefully you can see the poster, Nikita.
Yeah, I can see it.
Please go ahead.
Okay, so I'm a philosophy student and I wanted to look at social assistive care robots and trust. So I investigated philosophical accounts of trust and determined that they can't be used directly for SARs or social assistive care robots. So I came up with my own account of machine trust. So what are social assistive care robots? Well, they are robots that aid the elderly with daily tasks, such as making cups of tea, providing medical reminders, and dialing the emergency services. So a model that's currently being used is the CareRobot 3, which is in the little picture. And the widespread adoption of SARs can ease the burden on a healthcare system, and by assuming the role of a living caregiver. So it can provide 24-hour care and no breaks are required. So it can also be used to provide care for mild cognitive impairment and early dementia patients because they require the same assistance with daily tasks. So returning back to the main issue of trust, I looked at Catherine Hawley's philosophical account of trust and determined what the essential components of human trust are. So the first one is maintaining a tripartite relationship of trust, so having 3 different features. So if we have X as agent 1 and Y as agent 2 and Z as a task, it's agent 1 trusts agent 2 with a task. And there are 2 expectations of trust with any given task. So an agent must be capable of carrying out a task and they must be willing to carry out a task. So an issue that I wanted to avoid when coming up with an account of machine trust was applying human features to SARs. The reason being is because they are non-human entities. And if I was to do so, it would imply that they have a higher degree of agency than they actually possess, which is full agency. And full agency is only possessed by human beings. So full agency, or what I like to think of it is having full access to resources that allow one to act independently without any external influence on their agency. So SARs instead have minimal agency, which is merely just thinking about the capability to generate inputs into an output by fulfilling a task. So my account of machine trust can be used to describe the relationship of trust between a robot, a family member, and a patient. So we still maintain a tripartite relationship of X trusting Y with Z, but now Y is capable of taking care and addressing Z, and Y must address and take care of Z. So the capability of an agent also remains, but now willingness is not a part of machine trust. The reason being is because willingness is a part of free will, and free will is like other inner states, like consciousness, which are exclusively possessed by human beings. So if I was to try and put willingness into this account, I would be anthropomorphizing stars, and I do not want to do that. So it's best that I just leave that issue to the side. So if a robot uncontrollably starts moving around and commits an error and can no longer be used, who should be held responsible if this violation of trust occurs? Well, it's unreasonable to hold the SAR itself responsible because it's merely a machine. So I tried to come up with this notion of shared responsibility, where we could trace back responsibility to one or more human agents from the levels of pre-deployment to post-deployment. So this abstract model that I've drawn is just to merely identify an agent at each level, but it could be multiple agents at each level. So it could be agents A to E, someone who's a designer, a programmer, a manager, or a supervisor, and they can all share like a percentage of responsibility. So having this model can help us try to build an account of accountability and responsibility, which would ensure we can trust into social assistive care robots in the future. So to conclude, there are a few takeaway points, one of which is that we must treat SARs as separate entities. We must have a separate account of trust for them, which is different from human trust, and a system of accountability where we can hold a human agent responsible. And this is all to ensure that we avoid using human terms to social assistive care robots. I would also like to say thank you to Annette and Radu for helping me complete this project. Thank you so much for listening.
Thank you, Nikita. Okay, I was going to ask who your supervisors are. I see that, Annette and Radu. Thank you very much. Okay, so thank you. The next student is Patrick Lenezek. Is Patrick there?
Yes, good afternoon, I'm here.
Hello, Patrick. Hopefully you can see your poster there.
Yes.
Yeah, please go ahead.
Well, good afternoon. I'm Patrick Nenezich, a third-year natural scientist student who's specializing in nanoscience. And I've been working on a soft robot with the supervision of Mohamed Esfahani and Dr. Zayan Zeh. And basically, the idea was that to build a soft robot which can be actuated with an external magnetic field. And this, to my knowledge, did not exist before. These soft robots exist, but most of them are actuated with pneumatics. So yeah, and the other, there are magnetic soft robots, sorry. There are magnetic soft robots, but they are usually actuated with bulk magnets. So my approach was different. My idea was to embed nanoparticles, magnetic nanoparticles into PDMS, into the soft robot itself, align them in specific orders, and then actuate them with a magnetic field. As you can see on the pictures, those are the microscopic pictures of the carbonyl irons, which are embedded in PDMS. My first part of the project was to theoretically underlie the whole process and just calculate how these magnets would move with given magnetic fields. This took me some time, and then I could start actually building them. I built cantilevers because those were the most basic shapes to start with, cantilevers with different dimensions. And while the PDMS was cured, I placed them into a magnet, around 150 millitesla magnet, and therefore the carbonyl irons, which were already mixed into the PDMS, could align accordingly, so how I wanted them. The robot can move axially and or longitudinally when placed in an external magnetic field and changing variable magnetic field. It moves accordingly to my simulations. And the next step would have been to somehow put an electromagnet onto the PDMS, so we wouldn't even need an external magnetic source. I did the simulations for those as well and the theoretical underlying, but I couldn't realize it as I ran out of time. And looking at the time, I'm running out of time here now as well. So basically, I would like to thank my supervisors and Zion as well for providing me a place in the lab, as well as his PhD research team, who really helped me throughout the project with some stuff. Thank you very much.
Thank you very much, Patrick. Thank you. Now, everybody, this concludes the presentations from students. Just for clarification, we'll have another 4 presentations from supervisors of students, and we are very thankful that the supervisors come to represent their students where they couldn't come. Just to clarify also for the benefit of the panel, of course, we're not going to give prizes for best presentations to these very experienced academics. I'm sorry, you all very, very good presenters, as academics at the University of York are. But we are going to be judging the posters where the student, not the academic, provided the poster. They're still eligible for the best poster award. Okay, so thank you very much, everybody. So the first presenter is Nathan Wales for his student Daniel Matthewick's Dickinson. So Nathan, I can see you there. Let me just see if I can find your poster here.
Looks like it's number 10.
Number 10 there. Okay,
yeah.
Please.
All right, well, thank you all. And sorry that I don't get to have the award after all, but I'll still try to do my best. So I'm giving this on behalf of Dan. And Dan is really sad that he's not able to join us, but actually it's thanks to this to some extent. So he now has a job as an intern for robotics. So this actually got him into the next step. So really pleased for that. I'm in the archaeology department and we don't often use robots. And the other co-supervisor is Kirsty Pinkman in chemistry, where they do a bit more. But the object of this project was to use that robot that you see with the picture of Dan, which is a pipetting robot, and converting one of our methods that we use often in archaeology to something that can be automated. And that technique is called ZOOMS, which stands for Zooarchaeology by Mass Spectrometry. And basically it allows you to identify bone fragments to a species. So we look at collagen with mass spectrometry to have basically a fingerprint for different species. And we've used this technique quite a lot. And in that chart, you can see there's been like many publications in the last 10 years. This is something that was developed in York, but it has a limitation. And basically it's really, really tedious. There's a lot of pipetting. And so we bought this robot just before the pandemic. We didn't really get a chance to use it, but through Dan's work, we were able to find a way to basically automate most of these steps. And so he created a bunch of Python scripts, and you can see that little flow chart where basically every step in this process now can be done on the robot. And we now have the capacity to really increase the throughput and process tons of archaeological material to figure out interesting questions about the past. And I'm sure Dan will be very happy to take any questions if you want to email him.
Okay, all right. Thank you very much, Nathan. We're very happy to see the impact of the work and more roboticists around. Very good, thank you. Right, the next presentation is from Martin Trexler for Rebecca Wardle. I've seen Martin. Martin, where are you?
Hi, yeah, so I'm here.
Hi, Martin. That is Rebecca's poster. If you can see it, please.
Yeah, I can see that. Yeah, thanks very much. So yeah, hello. So it's also a shame that Rebecca can't be here. So she's enjoyed the project very much, but she's been roped into something else actually. So the Rebecca's project was about hi-fi, lo-fi sensors, and we titled it "Losing Your Senses," because the goal of the project was to investigate or to create a robot that has better proprioception than current robots have. And that was in order to increase their capabilities to behave autonomously and to adapt in different situations. To give you an example from real world, I mean, I hope that everybody occasionally wakes up at night and has to go to the loo or has the craving of a chocolate bar or something like that. And we as humans, we can get up at night and find our way through our flat or house at night by relying on our bodies, essentially, as sensors. So we rely on touch, we memorize where we left things. So we usually don't bump into doors, we usually don't bump into other people's beds and wake everybody up. So we are kind of capable of navigating in a scenario in a completely different context than we normally see it. So during the day, we use mainly our eyes, and we rely on vision mainly to make sense of the world and to find our way around. So this project is now therefore using a hi-fi sensor, which we selected a LiDAR as, which is kind of a very accurate distance sensor, and lo-fi sensors, which were these sharp IR sensors, which are pretty rubbish. Everybody who has worked with robots will agree on. And the idea was to use a robot controller, which is based on a kind of a neuromorphic architecture, which is reservoir computing, but that is a different topic. That's a computational model, but that can be trained. And our idea in the project was to see whether we can train this neuromorphic system using data from the hi-fi system, the hi-fi sensors, sorry, and the lo-fi sensors, and then actually recall navigation capability if we switch the hi-fi sensor off. Now, Rebecca's done a splendid job actually in getting all the hardware interfaced and working, and it was a challenging time for things like that, as we've heard that before. So she did a splendid job, actually got it working, so the robot was able to roam around in her flat, essentially. And she's also trained a reservoir on the two different sensors. We didn't quite get it to the point where we could then switch the hi-fi sensors off, but the robot platform is really at a stage, and we have done initial experiments that look really promising, and we hope to find a victim next year as well to carry on the work. So thank you very much to the venerable studentship that provides every year like all these nice projects and the possibility for the students to undertake these projects. Thanks to Rebecca, and the other co-supervisors except me were Matt Dale from CS and Susan Stepney from CS. So please do get in touch if you have any questions. Rebecca will be happy to kind of chat and reply to emails.
Thank you, Martin. Thank you very much. Okay, the next presentation. I think I've seen you who there. Who are you? Are you all right to go down?
Sure, yeah. I'm okay. Yeah, right now. Yeah.
So you who is here for Jonah, young husband, and where is your poster?
Okay, so the young husband is ambassador for the university for new entrant students. So and so he's not available here. Just crash with this event.
Right. I don't think we have a poster for him, do we?
So if you don't mind, I can share my screen. I have his.
Please.
Okay. So right now you can see this screen. So may I start?
Yes, please.
Okay, thank you. So thank you, Anna. So thank you for your robot project. This is year one student work for me for this project. So the background of the project is about the motor drives for the robots. We are electrical engineering. So in our eye, so robotics is composed by many motion control of powertrain plus high advanced control algorithm. So we down to the physical layer. So we consider about the uncertainty of the powertrain. And here this student work consider about uncertainty, or we say accuracy, sensors on accuracy. For example, in the powertrain, we have a lot of sensors in the for the motors. If we can see the extreme condition, the sensor will not give accurate information for the controller. So we hope the students help us to investigate the influence of the inaccurate sensors information in the control loop. That may result in vibration and the hesitation of the control speed. So this is the the simulation result from the MATLAB. The students, have very good progress on the basic, knowledge of remote control. In the next stage, so we will investigate any mitigation strategies to the sensors, accuracy uncertainty for the powertrain. Okay, thank you.
Okay, thank you very much, Uhua. Thank you.
Thank you. I stop share.
Thank you.
Okay.
Our last presentation now is by Edgar Buchanan. I can see Edgar there. Edgar, I don't think we have a poster for your student whose name is Jasmine Poihonen. Poihonen. Have you got a poster?
No, we don't have a poster from her, but I can share an image of the project from my screen. Is that all right?
Yes, please go ahead.
Right, so Jasmine unfortunately couldn't present her poster today, but I'm gonna give a very brief description about the project that she was working on. The project that she was working on is called Autonomous Robot Evolution. And in this project, there are three main stages. There is the first stage where the robots are designed by an EA, the second stage where the robot is fabricated in an autonomous way, and the third stage where the robot operates and performs a task. In Jasmine's work, the objective that she was studying is what happens if you modify the environments where the robots are operating and how this influences their morphology and the controllers of the robots themselves. So in the findings that this is in the training facility that you're seeing on the screen right now. And in her findings, she discovered that the scenarios, they don't affect much as the tasks that robots are performing. So if the robot is performing one task and the second robot is performing a different task, the morphology is going to change, whereas the scenario doesn't. And just to make the distinction, scenarios means that you can move objects around, whereas a task is the objective of the robot itself that it has to operate. So yeah, that's in a nutshell. If anyone has any questions, I'll be the breakout room.
Okay, all right, thank you very much, Edgar. Now we are surprisingly almost on time, with 3 minutes late. I wouldn't like to cut short the time that we all have to go and visit the students and their supervisors and ask questions and find out about this plethora of very varied and very wonderful work that's being done. So I would say that we push forward the start of the presentation. So Alvaro, if you could please start a presentation at 4:20. So, and everybody please meet again here at 4:20 to listen to Alvaro and then to see the result of the decisions by the panel. Please take the time to go ahead and talk to everybody. The students have worked hard. The students have done fantastic work. Let's go and talk to them and find out more about their motivations. Okay, see you back here at 4:20.
Yes.
Okay, cool. Thank you. So I'll present today the approach that has been developed within a group of projects in the Department of Computer Science and Electronic Engineering here in York. And then I'll focus more on one of the notations that we have developed to support this approach. So I'll quickly introduce the approach, then the notation, then I'll describe the semantics, the meaning of this notation, the tool support that's available, and then conclude and discuss a little bit some of the projects that have been developed after Robochart and that are being developed now as well. So the motivation for this work was that we noticed, talking to roboticists, but also reading the literature, that there was a pattern of development in the robotics community that was, to a certain point, similar to what was done for non-robotic software, but that didn't take advantage of everything that was developed during this work. So you had developers having a first phase where an abstract model would be developed, like a state machine, for example. If you don't know what a state machine is, I'll show it a little bit later. But describing kind of diagrammatic, creating diagrammatic models, usually as drawings of how these systems were supposed to behave. Then from that kind of abstract and informal design of a system, they would develop simulations implemented directly in code, usually tailored to either a particular hardware or a particular simulation environment. And once they were satisfied that the simulation was giving adequate results, they would either try to adapt that code of the simulation or rewrite the code completely to fit into a particular robot and in a particular environment. And that also involved a lot of tweaking the code. So one of the aspects that was not explored in this kind of approach was traceability, in a sense. So you would start with a state machine, a drawing of a state machine, then you draw a simulation, you throw away your state machine, then you create your deployment code and you throw away your simulation. If you find an error in either the simulation or in the deployed code, you basically need to go back and redo a lot of stuff. So what we wanted to support was an approach that would allow people to not throw away stuff that they have done already, and also help with the checking of the simulations and of the deployment. So one of the things that we observed in the literature, and I think one of the posters today had an example of a flow chart, was that diagrammatic notations are often used at least to record, illustrate, and explain the designs of these robotic systems. So it is a notation that is usually used informally, but roboticists tend to understand it. Now there's these notations are usually used in an informal way, and the negative part of this is that there's a lot of lost potential. So in principle, you could take a state machine and use it to generate tests, to generate code automatically, to verify it using some model checkers and theory improvers, and that doesn't seem to be quite the case in the robotics community. You see that more within software engineering, and that's what we're trying to bring to the domain of robotics. So just an example of a state machine that's a very complex state machine from a paper from colleagues in electronic engineering. And there are obvious advantages to this kind of notation. It's a lot easier to follow and kind of follow the flow of execution and understand what's going on, but they also can grow quite a bit. The notations tend to be, especially on papers, they tend to be a little bit too informal with some information missing, and all of that needs to be addressed if we really want to take advantage of these models. So the objective of the first project, RoboCalc, was to design graphical notations that had formal semantics and were specialized so that they both tractable in terms of verification and analysis, but also in terms of what roboticists understand and already know, but also being comprehensive enough to support development of realistic case studies. And then finally, we wanted to support simulation, analysis, and verification. So the approach that we developed was based on models. And the idea would be that we start with this, what we're calling a Robochart model, and I'll describe Robochart a little bit later. And so we would start with a model in Robochart in a language that roboticists are already familiar with. And then we would automatically generate a proof model, a mathematical model that describes the meaning of these Robochart models. And the idea here is that if you don't know the mathematical models that underlie Robochart, you shouldn't need to look at them. So it should be generated automatically and analyzed automatically as well. So that kind of proof model would then be fed into model checkers and theory improvers, which would also receive some properties of interest. And hopefully, in the case of the model checkers, always check automatically. In the case of theorem provers, you may need to provide some help, but hopefully you get a result saying whether the properties of interest are valid or not. Now, if they're not valid, you usually will get some evidence from a model checker, for example, that tells you why it's not valid. And then you can go back into the Robochart model, modify it to fix whatever problem you found, and then run up from the Robochart model to the validity check automatically again until you get a model that's valid according to your properties of interest. So at that point, you could automatically generate a model in another language, a sister language of Robochart that we're calling here RoboSim. And the characteristic of this language is that it embeds a cyclic behavior, a cyclic architecture into the software of your robot, so that it's closer to what we observe in simulation. So if the model is valid, you automatically generate this RoboSim model, and then you use another automatic generator to generate code that fits into one of the used simulators. We've been using mainly Gazebo, Argos, and CopiliaSim. And then you could use that to simulate your application, check if the simulation is valid or not. Again, if it's not valid, you can either go back all the way to the Robochart model. You can go back to the Robochart model, fix whatever the problem is, and go back to where you were simulating automatically without much effort. If you decide that your simulation is suitable, you can automatically generate deployment code, which then would be deployed into a real robot and used for testing the robot in particular environments. Now, we could also use Robochart, that model that we had in the beginning, complemented with a description of the environment, to generate test cases that then can be fed into the system that we're testing. And we get a last point where we're checking for correctness. And in this case, again, if we're not happy with the results, we can go back to the Robochart model, adapt it, run this flow chart again completely automatically until we get a result that we're happy with. And in this case, we have a collection of resources that we can use to try, for example, to certify the software and the application in general. So you'd have automatically generated code, you could have proofs, you could have test results, assumptions, environment restrictions, all of those things. So central to that approach is this language that we're calling Robochart. Now, Robochart is basically a language based on state machines with a little bit of structure around them, but that also supports time and probability, a specification of time and probability properties, for example. So the formal semantics of Robochart is given in three flavors, although the main ones will be timed and probabilistic. We also provide something that ignores time so that it makes analysis easier. But the most important ones are the timed semantics and the probability semantics, probabilistic semantics, that allow you to verify properties that take into account time and probability. Robochart has a number of well-formed conditions that tell you that a model is well-formed, that it makes sense, and that semantics can be generated for it. And it also has some tool support in the form of a graphical editor for modeling, a validator that implements these well-formed conditions, and a number of code generators to produce both the mathematical semantics and simulation code. Now, the main construct of Robochart is a module, and that basically encapsulates an application, a single robot. It will have something that we call a robotic platform and one or more controllers that run in parallel. Communication between this robotic platform and the controllers is done via events that can be either synchronous or asynchronous. And robotic platforms can share can provide shared variables that the controllers can use to interact. Now, the robotic platform is basically a very thin layer that describes assumptions that are made about the robot hardware. So you can describe a hardware here, for example, the foraging RP, as having a variable distance, a constant called nest, and some operations that are provided by these interfaces, movement and grasp. So it's an abstraction of what a real hardware is. And it basically is just saying what kind of services are provided that the software can take advantage of. The idea here is that it should be completely independent of the controller and of the state machines. And provided that certain conditions are met, we should be able to switch the platform or combine with different controllers and state machines to create a new application. Now, the controller is the highest level of behavior that we can specify. And it basically contains a number of state machines that can be that are running parallel. It can define operations that these state machines can use. And it also defines variables and events. The variables would be shared between the state machines, and the events are used to communicate with the external world, in particular with other controllers or the robotic platform. Now, the state machine is where the core of the behavior of an application will be. So it's primarily a sequential description with a little bit of parallelism in a particular place that I'll mention later. But it basically allows you to describe the flow of execution of your application in terms of states, junctions, and transitions. So we can have simple states, which are the ones that are shown in this figure. We can have composite states, which are basically states that have almost like a complete state machine inside. And you can have final states that describe termination in a sense. We can also have initial junctions, junctions and normal junctions. And these junctions provide a way of controlling the flow. So you could have almost like an if statement saying, if you get here and the condition is valid, you go to one place, otherwise you go to another place. And you can create loops with that as well. States can have actions. So you can have an action that's executed when a state is entered, an action that's executed when it's exited, and also a during action that's executed while the state is being executed. So this during action is a point where you can introduce some parallelism in your models. And it can also have the local variables, clocks like this T here in this state machine that allow you to talk about waiting for a certain period of time or setting up deadlines for certain actions to occur. Now, the types in the action language of Robochart are basically the types of Z, which is a formal notation. And the action language is a very simple imperative language with just assignments, event signaling, operation calls, and sequential composition. Now, the semantics of this language is formalized into a formal notation called CSP, which allows you to describe sequential processes that interact in parallel and communicate via events. Now, we cover all of the language, so modules, robotic platforms, controllers, and state machines with this language, with the semantics. And it has a structure a little bit like this. That's not too important here, but basically what you have is a compositional semantics where we can derive the meaning of a controller or the meaning of a state or state machine and combine them in parallel to form the meaning of the whole system. So it's for the module, it's the combination of the meanings of the different controllers. For the controller, the semantics is the parallel composition of the semantics of the state machines, and similarly for states. Now, the action language, as I said, was very simple and it has almost like a direct representation into CSP. So we have operation calls correspond to process calls, event signaling corresponds to communication on event channels, and assignments. That's a place where it's a little bit different, but it basically corresponds to communication to a memory process. Now, if you don't know CSP, you might know a language called Go, and it has a very similar communication paradigm. Now, RoboTool takes all of these features and implements it as Eclipse plugins. So it provides a textual editor for Robochart that's based on a tool called Xtext, and also a graphical editor that's developed using another tool called Sirius. It has a number of code generators that produce both all the semantics, the untimed, the timed, and probabilistic semantics, and also has a code generator for simulation. It also implements all of the well-formed conditions that we have for Robochart, so that you can check easily whether your models are well-formed or not. So here's just a quick screenshot of RoboTool. As you can see, you can edit either textually or graphically, and you can generate code from that, the code and the semantics. Now, we have implemented a number of case studies, including like basic algorithms like the alpha algorithms, the chemical detector, which is an example that was developed by our colleagues in the electronic engineering department, and various others. There's a page here on the footnotes. If you want to see what kind of case studies we have developed, you can look there. And one of the key aspects of the tool is that it allows you to generate automatically the semantics of Robochart that then can be fed into a tool called FDR4, which is a refinement checker. And there you can feed in properties like asking whether your application will deadlock, or whether there's an infinite loop, or even more specific properties. We have an assertion language that was developed to help you write these properties without really knowing CSP, and that was very basic. And now there's one of our colleagues is developing it further to allow you to describe, for example, sequence diagrams that describe desirable runs of your application. Now, this is the basic support that we have within RoboTool. You can start from Robochart models. You can then generate CSP that can be used in FDR and the theorem prover Isobel Hall. Or you can generate models that are suitable for Prism, which is a model checker for probabilistic models. Or you can generate, for example, C++ that can run in Argos. So this is just a quick conclusion that what we have developed so far. There's Robochart to model state machines, including time and probability. It has a formal semantics in CSP. And there's tool support for modeling, verification, and simulation. Now, since that work was first done, we have developed a lot more generators in particular. So we can have generations of simulations now for the RoboSim notation that's been implemented. We have an automatic generator for the probabilistic semantics. We're working on generating the semantics to be used with the theorem prover Isobel UTP. We have other notations that have been developed, so RoboSim that I already mentioned, that's kind of dedicated for simulation. We also have languages for modeling robotic hardware. We have work being done on modeling environment. And all of those models are being integrated so that we can generate and analyze the systems in more and more complex scenarios. So that's what I have to say. Thank you. Any questions? I'm happy to answer them.
It seems like I just joined as Alvaro was asking if there were any questions.
Yes.
Are there any questions for Alvaro? I think, Alvaro, everybody wants to know the result, isn't it?
The result
of the prizes for the students.
Oh, yeah.
Okay. Thank you very much, Alvaro. I'm sorry we had to miss your presentation. Johnny, could you please bring back the other judges to the main room? Are they here now?
Are they stuck in the room, are they?
Keith is here.
No, I'm here.
No, I think they're both. I think Keith and Darren are here.
Okay. Guys, thank you so much for waiting. Thanks for joining us. Thanks for being here, waiting for the result. The judging panel had such a very, very, very hard time. And I'm not saying this just to be nice. We were all very, very impressed by the quality and the variety of the work. Lots of the students have plans even to continue. We saw students that now have a job in the area, and applications are very, very exciting. And I think Keith and Darren want to say a few words as well, their impression of the work that's been done in the scheme. Darren.
Yep. Well, I just wanted to say thank you to everyone. It was great fun hearing your presentations and looking at your posters. Really impressive range of work. And as a social scientist, thank you for making it very understandable and engaging. I just wanted to say thank you. Thank you for the opportunity to come and see you all and all your work. Really interesting stuff.
Thank you, Darren. Keith?
Yeah, just to reiterate, I mean, it's been a fantastically interesting afternoon watching your presentations and really engaging with your posters. As has been said, an amazing array of different approaches, different questions considered, and overall just such a high quality bar from every single project. We've had really interesting discussions in the judges' rooms about every single one of these projects. So everyone should be incredibly proud. And as I say, as Darren said, thank you very much for sharing your research with us.
Yeah. And thank you, Keith, and thank you to the judging panel for helping with this such a hard decision. We wish we could give a prize to everybody. Everybody's going to get a certificate, and I hope that everybody, will continue working in the area of robotics, because you've clearly shown that you have the talent, and continue to contribute to this fascinating area. We have a bit of a cop-out. We are now going to give 4 prizes: the best presentation, the best poster, the best work focused on social sciences, and the best work focused on engineering. One thing that we focused on to help us to distinguish all this wonderful piece of work was the ability to appeal to a multidisciplinary team. So you have, as I said at the beginning, the judging panel, myself as a computer scientist, a philosopher and a sociologist, and that was basically, we tried to pick out those that we could all understand, that we could all defend, that we all liked, in spite of not necessarily being in our area of expertise. So the first prize I'd like to announce is the prize for the best presentation. And that prize goes to Isobel Stanton for her poster on robot-assisted surgery, a waste of resources or the future of healthcare. Izzy, is she here? Congratulations.
Thank you. I'm so grateful. Thank you.
Very well done. Very good presentation. Very clear. Thank you so much. Our next prize is for the best poster. The best poster goes to somebody who is unfortunately not here, but did send a poster that was kindly presented by the supervisor, and that is Daniel Matthewick's Dickinson for his work RoboZooms, Automating Ancient Bone Identification. Very well, please, Nathan, could you please pass on our congratulations to Daniel? And,
yes, I will do. Well, thank you for picking that. I've been very impressed with him too, so thank you.
Thank you. Congratulations. Congratulations for you as well. Okay, and now the biggest cop-out of the day is the best work on social science focus and best work on engineering focus. That's basically because we wanted to give a prize to everybody. If we could have invented 10 titles of best something, we would have done, I think. But the best work that we have identified is the work of Emily Wood on investigating social robots. Congratulations to Emily and to her supervisors. We found that it was particularly clear the method that was used and the achievements that were made. Congratulations, Emily. I hope
Thank you.
I hope
Thank you so much.
Enthusiastic and working in this area. Congratulations.
Thank you. Thanks.
And last but not least at all, the best work on and with an engineering focus that goes to William Burbidge for his work on supercapacity powered robotics. Congratulations, William. I'm not. I can see William there. Congratulations. Very, very good. Very, very well done. Okay. Thank you. Thanks for your time, everybody. And you are all winners. And I think the University of York is enriched by your work and by having you as a student. Thank you so much. Congratulations to all. Congratulations to the supervisors as well. And I hope to see you next year. If you're still a student, don't forget to come along and support the next generations of Venables students. Thank you. Thank you, everybody. Good afternoon.